afternoon, ladies and gentlemen. My name is Dr. John Belkowitz, and we're here at Intelligent Concrete talking about the magical world of concrete. It's Math Monday, so strap yourself in, and here we go. So we're talking about colloidal silica used for alkali silica reactivity mitigation and what that expansion looks like with and without colloidal silica. And today we're just going to focus on colloidal silica, but we've got a lot of detailed data sets that go into the different types of colloidal silica and then with and without Class F fly ash. So a lot of great data we're excited to get into, but today we're going to focus on just the ASR with and without colloidal silica. Okay, so first, quick definition of alkali silica reactivity. Here in Colorado, in the Western U.S. business unit, and throughout a major part of the known world, we have these types of aggregate that are out there that have a very reactive type of silica. When I say reactive, when they're in the presence of moisture and soluble alkalis, specifically the ones we see in concrete like sodium, potassium, and sometimes calcium, we get this expansive gel that grows at the base of the aggregate because these alkalis kind of consume the silica, create this expansive gel that happens at the interfacial zone between the aggregate and the hydrated cement matrix, that binding matrix of our concrete composite. And when that gel grows, it gets confined, it develops these residual stresses that eventually overcomes the shear and tensile capacity of the concrete. In doing so, it starts cracking from within, more water comes in, and it gets really, really nasty. So we have a lot of structures that might not have ASR as the primary failure mechanism, but that ASR failure does lead to either steel corrosion, chloride attack, and then steel corrosion, or de-icing salt attack, but it ultimately causes premature failure, and then we've got to rip and strip and replace it, or at the very least, repair it. So our biggest problem in the concrete industry is since about 1978, we've been going away from coal combustion as our primary use for energy production. And we can't undo that, and because of that, the specific type of coal combustion residue that we've hung our hats on for the last how many decades, we just don't have as much of it. And we're going to have a wonderful video on that, so please stay tuned, but ultimately the same volumes and the same quality that we used to rely on to mitigate ASR, it's just not there anymore, especially out here in the Western U.S. business unit. So with that, folks still have to get the concrete out the door, and if it doesn't have that mitigating material, we're eventually going to see concrete structures that don't last as long. And in some places it happens a lot faster. We start noticing it faster. In other places we're going to start noticing it maybe 3 to 10 years from now. Okay, so what is the resolution? What is the answer to this? So I'm going to dive in to my PhD here because the answer that I'm going after, the rhetorical question was, the answer to this is colloidal silica. Whether it's to enhance it on the concrete on its own or to be used in conjunction with a supplementary cementitious material like a crappy Class F fly ash, slag, silica fume, metakaolin, whatever your fancy is, using colloidal silica to enhance those other materials is absolutely awesome. And we go over both of those in my PhD. I go over both of those in the PhD. And also Whitney helped out a lot, so definitely we. So when using colloidal silica, what we looked at was a bunch of different approaches. We started with ASTMC 1567 and 1260. It's a mortar bar test. You're looking at the concrete over 28 days. You're making 3 mortar bars that are being stored in a sodium hydroxide solution that I believe has a 4 molarity, and it's kept at a temperature of 175 degrees Celsius. I'll have to double check on those numbers. And 176.6 degrees Fahrenheit. Is that it? Anyway, yeah, 80 degrees Celsius. So basically what we saw from this, if you look at the first graphs, what we did is each one of these graphs, we put the straight cement, the 20% Class F fly ash replacement, and then we did 3 dosages of nanosilica, and we had, 4 dosages of nanosilica. So dose 1, dose 1 for the small, medium, and large size particles, which was CS1, 2, and 3, and CS1 was a 3 to 5 nanometer, CS2 was a 15 to 17, and CS3 was a 45 to 47 nanometer particle. And what you can see is, through the different charts, is that the smaller particle at lower dosages was really great at reducing expansion at the earlier ages. But as time progressed, the class F fly ash as well as the other colloidal silica mixes almost had a chance to really catch up to the colloidal silica dose 1 and dose 2 and dose 3. But as we went up to the higher dosages, the colloidal silica, that smaller particle, didn't do as well. And at a certain point, it's almost as if it's better not to have that smallest particle in there when we get up to the dose 4. And that's something that manifested from mixing up that smaller particle at such a higher dosage. Especially with concrete mixers, we're not putting in enough energy to break up the agglomerates, especially when we go over 1%, we go around that 2%, and we did an entire study on that to look at the agglomeration or the impact of that particle size on the agglomeration or the pore dispersion of those nanosilica sized particles in the hydrated cement matrix in a fresh state and a hardened state. And as we increase the particle size, you are getting to a larger particle, meaning you don't have as much reactive surface area. With the smallest particle that had a 3 to 5 nanometer, it had a surface area of 500 meters squared per gram, and the largest particle had a surface area of 80 meters squared per gram. That being said, even the larger particle, forget the available surface area for pozzolanic reaction, but just because it's a larger particle, it's not going to have as great of an impact through heterogeneous nucleation just because it's such a larger particle. And because of that, because it's not going to have as much of an impact, because it has a larger force field, a larger or a smaller manufactured force field, but a much stronger electrical double layer at the surface, just because it is a larger particle, it's going to react at a later rate or a slower rate than the smaller nanoparticle. And that being said, it's going to have an impact at later ages. And this is something that we see, when we look at the later ages, or the highest dosage of that larger particle at the 28 day, it's knocking it out of the park. It's just, you really don't need anything else to mitigate that ASR. If you can use that larger particle at that 10.92%, the unfortunate reality is using that larger particle at 10.92%, your fluid concrete gets turned into cotton candy. It's just too sticky, the viscosity of it changes, the rheology of it changes, that it's not practical, and 10.92% is so gosh darn expensive that it's not a viable, scalable solution for the back of the ready-mix truck. So despite the fact that, hey, bookcrete, labcrete, it looks awesome, realcrete, it wouldn't work. And that's why we don't see this concept, this 45 to 47 nanometer at 10.92%, which I believe is around 20 or 30 gallons, so it's even difficult to get into the back of the truck per cubic yard. So, yeah, how did I do?
Excellent.
She's the best. So thanks for joining us today. We're excited to go over more detail and more information about using colloidal silica to mitigate. We've got a lot of work that we did that led up to our patent and a lot of information to share. So thanks for joining. Don't forget to like and subscribe. Ding that bell for notification. Go, go, great!